In this Part 2, Similarity Search, using generative AI with vector embeddings video, we will deep dive how similarity search is achieved using generative AI with vector embeddings, various embedding models, Cohere, OpenAI, Hugging Face, TensorFlow, PyTorch details, the vector databases which are optimized for similarity searches. For example, AstraDB, Pinecone, Weaviate, Milvus. Process flow. Data ingestion. The process begins with input data, such as images, documents, or audio files which are fed into the system. These are the raw data sources from which features are extracted. Embedding generation. The input data is passed through an embedding model, which could be based on models from popular AI frameworks or services like Cohere, OpenAI, Hugging Face, TensorFlow, or PyTorch. These models generate vector embeddings for each piece of data. A vector embedding is a numerical representation of the content, image, text, or audio, that captures its semantic meaning. Passed through an embedding model that transforms them into numerical vector representations, vector embeddings. Storage in vector database. The generated vector embeddings are stored in a vector database. This database is optimized for similarity searches, for example, Pinecone, Weaviate, Milvus. The vectors are indexed so that similar items can be quickly retrieved based on distance or similarity measures. The database supports efficient querying to find items similar to the user's query by comparing the query vector with existing vectors in the database. Query embedding model. A query is passed through an embedding model to convert it into a vector format. For example, a user might search for images, documents, or audio similar to a specific query. The embedding model transforms the query into a vector like 0.9 minus 0.7 minus 1.0 minus 0. 8. When a user makes a query, such as searching for similar images or documents, the query is converted into a vector using the same or similar embedding model. Similarity search. The query vector is then compared with the stored vectors using KNN, K nearest neighbors, or similar algorithms to find the closest matches. KNN measures the distance between the query vector and vectors stored in the database. For example, using cosine similarity, Euclidean distance. Vectors that are nearest, most similar to the query vector, are retrieved. The query vector is compared with stored vectors in the database using a similarity algorithm, like KNN. The algorithm identifies vectors that are closest to the query vector. Return results. The system returns the most similar items, query results, based on the vector comparison. This process allows for fast and efficient retrieval of similar items based on the content's meaning, which is crucial for applications like recommendation systems, search engines, and multimedia retrieval.
Let's take a use case of generative AI product catalog system for similar visual search, focusing on how similar items are identified and displayed within a product catalog. Here's a breakdown of the components, process flow, and data flow. These are clothing products, where each item is visually represented with an image, product name, and possibly other attributes like price and description. A user is selecting an image of a product, which is termed as the query image. Once a query image is selected, the system will find the top K most visually similar items from the catalog. In the example, the visually similar products are presented next to the query image. Each item in the similar results includes a thumbnail and product description, for example, similar shirts, shorts. View Similar button. The View Similar button under each product is an option for users to find more products that are visually similar to the current product being viewed. This allows users to expand their search based on their preferences. Models per product. There's also a note about potentially expanding the number of models per product. This indicates that the system might offer various visual representations for each product, perhaps showcasing different sizes, colors, or fits. Visual embedding generation. The selected product's image is passed through a visual embedding model, such as one based on computer vision, that extracts features from the image and generates a vector embedding. This embedding encodes the visual characteristics of the product, for example, color, style, shape. Similar product search. The vector embedding of the query image is compared with embeddings of other products in the catalog. Using similarity algorithms like cosine similarity or Euclidean distance, the system identifies the top K visually similar products, for example, other shirts with similar patterns or colors. Display similar products. The system displays the most similar products next to the query image. Each similar product is shown with an image, product name, and possibly a price. In this example, multiple red shirts and similar clothing items are returned as the result of the query. User interaction. The user can continue exploring by clicking the View Similar button to find more products similar to the ones they are viewing. This feature allows users to refine their search and discover items they may not have initially considered. Use case and benefits. Visual similarity search is particularly useful in fashion e-commerce, where users are often looking for products that match certain visual preferences, for example, color, pattern, or style. This system allows users to efficiently navigate large catalogs by focusing on visually similar products, improving product discovery, and the overall shopping experience. The potential to expand the number of models per product suggests further personalization, such as offering more diverse models in terms of body type, complexion, or outfit combinations, which enhances the inclusivity and variety of the shopping experience.
Thank you for watching this video.